Today he will talk to you about plasma thunder, Mars in a week. He describes it as an application development of the super ion drive, and it's presented. Beginning with the equation governing the transfer of kinetic energy from the engine to a hypothetical large space vessel, projections for fuel requirements, matter energy conversion rates, thrust levels and durations, and other important parameters are determined for a manned mission to Mars. Variations on two different interplanetary flight scenarios based on two different designs for the spacecraft are considered. One case involves the spacecraft having a mass of over 100 metric tons, reaching Mars from Earth in just 7 days, using less than 50 kilograms of fuel. Cases for spacecraft with masses ranging from 1,000 to 50,000 metric tons are included. And I now turn it over to Mark Solis, your speaker.
Okay, basically, what I want to do is tell you a little something about what is called the plasma thunder engine, previously known as the super ion drive, which I spoke about in Toronto. This is a concept which goes back a little less than 2 years ago. What it is, basically, is a way to hot rod an ion engine. And the present configuration calls for the integration of some 7 technologies. And those technologies are the conventional ion engine as a plasma injector, the O'Neill mass driver, plasma magnetohydrodynamic technology, or MPD, magnetoplasma dynamic technology as it's known now, the Newman machine or declension magneto, cryogenically cooled superconducting coils, the quantum effect bipolar junction transistor known as the QEBJT or simply QET, and the micro supercomputer. Now, a portion of the plasma thunder engine following the plasma injector is called the interactor or interactor assembly. And this is where useful thrust is developed. This is a basic block diagram of a plasma thunder engine. The interactor assembly, you have a flow sensor over here which provides information to the computer, which controls the behavior of the interactor. You have your fuel over here, which is converted to plasma by the ion engine, injected into the interactor, which is essentially a long array of magnetic accelerators which use something called mutual field hyperdeclension. Now, the term declension means collapse. When you're dealing with a magnetic field about an inductor, the field can be expanding or collapsing. When it is collapsing, we say we have a declension field. If it's collapsing into an open circuit or into a resistive or a reactive load of some type. If there is no load whatsoever, but a dead short, you get a hyperdeclension, a very fast collapse of the field, because this is one of the 2 discontinuities in the T equals L over R relationship for you engineers. You have one that occurs where R equals 0 and one for R at infinity. The field behaves the same way at both ends. It would not appear that way as R goes to 0 because your time would be increasing, but when you reach the discontinuity, the curve drops off again. This sort of behavior has been observed in the Newman machine, and you can demonstrate it by firing an electron plasma beam across a coil and then doing this sort of thing and watching the plasma as it is first driven away from the coil by the expanding field, then drop towards the coil when you short it. Now, what happens in this interactor, basically, is that as energy is drawn from the plasma itself by this mutual field hyperdeclension, the plasma is accelerated by its own energy. This energy is coming ultimately from the weak nuclear field by way of the electroweak coupling, ultimately to electron spin conserved under a supersymmetry, and therefore to the magnetic field of the outside world. Through this mutual field hyperdeclension, it tries to do work against a dead short. The energy has to go somewhere. There's nothing there. You get a reaction in the plasma, just like you do between a rotating permanent magnet and the impeller coil in a Newman machine, where the magnet accelerates with the coil shorting. The same kind of interaction, by the way, takes place in an AC transformer if you short the secondary. This has been going on in front of people all these years, and they never realized the significance of it. If you were to take the primary and your power source and replace that with a rotating permanent magnet or a moving plasma, and then apply supersymmetry so that you don't have to worry about the fact that electron spin must be conserved, and if it's conserved under ordinary symmetry, then it cannot act as an energy gateway, but with supersymmetry it can. It can have the appearance of conservation and yet act as an energy gateway. That is the key to the function of this engine. Now, the purpose of the present paper is to show you what you can achieve with this kind of technology. This is matter energy conversion being done directly in this interactor. But I keep the rates to 10% and below. I deal with only 1% and 10%. I have 5 scenarios, 3 different ships, 2 of them manned, 1 unmanned. Let's look at our first scenario. Let's look at the slides and see what we have coming up. This is, before I go on, this is a schematic diagram of an electronic version of a Newman machine. I actually built one of these things, 2 different ones, and tested it out using little toy Mabuchi motors. And I made measurements, and on average, I got 2.5 times the power out that I was putting into the motor. So the magnet was actually doing work against the external world. Very, very interesting machine. And by the way, insofar as you have an entropy path and you have an energy source, this is not in any way a violation of your first and second laws of thermodynamics. What they're telling you, if you have a black box, you put in a unit of energy, you get out 10, you put in 2, you get out 20, is that there's an energy source in the box. What you're supposed to do is find it. You would not believe how many people with PhDs, 40 years in the field, Oak Ridge fellowships, and the whole 9 yards, flunked that little test. They should be thankful I was not their graduate advisor. They would not have gotten their degrees. This is the significance of being able to travel at extreme speed with a large payload. This is something which plasma thunder will do for you. It can move a very big ship a long way very, very fast. How many people were in Mark Millis, is it his last name? The fellow who did the presentation the other day about warp drive, when? Remember the diagram he had up there? That's good, thank you. It's about half the room. He had a little diagram that showed the envelope with the thrust versus specific impulse, and the higher the specific impulse, the lower the thrust, until finally you're talking about, he said plasma drives generally. He was talking about just a conventional ion engine, where sure, you have this considerable specific impulse, but the thrust is measured in ounces, this kind of thing, millinewtons, things like that. Well, the plasma thunder engine blows all that away. It goes up here on his diagram. Also, 50,000 seconds is about 1/10 of what you normally achieve with a plasma thunder engine using a fuel tank, which in terms of its liquid capacity would be around 50 US gallons. We're going back and forth between here and Mars repeatedly with a vessel that weighs 1,000 metric tons and has 10 people on board. Now here, typically when they send a probe to Mars, any kind of a ship, they take about 2 years. They launch out of low Earth orbit, they use conventional propulsion technology, chemical rockets, and they go around and around and around and around and around and around and around, and ultimately they get there. But the more thrust you have and the longer you can keep it up, especially if you can do an accelerate halfway, decelerate the rest of the way type routine, which people have been wanting for a long time to do, but they didn't have an engine to do it, except of course just the ion engine for small payloads. The faster you can go from point A to point B, notice it says high delta V, the more closely your flight path is going to resemble a straight line directly from there to there. So instead of saying, well, Mars will be over here if we launch now, and oh, it's over here now, but it's going to be over there. We'll hit it right about here. And they do these massive calculations compensating for all the bodies in the solar system and various and sundry other perturbations passing of asteroids, comets, and what have you, especially if you're going to Mars. You have to go through the asteroid belt, you know. Or is that right? Or is the asteroid belt between Mars and Jupiter? Did I get that wrong?
Yes.
Ah, I bite my tongue thusly. My apologies for the error. Well, you probably have to pass a couple of Apollo asteroids while you're at it because they come down our way, don't they? They're bigger. Well, anyway, you have to compensate for all that mess, and you ultimately end up here. So you kind of wobble your way along, and you ultimately end up here. And you have so-called mid-course corrections every few million miles. But this is ideal if you can do it. Plasma thunder can do it. This is another representation of that sort of thing. AOS means average orbital separation. Now, at opposition, this distance is only about 1/5 of what you see here. Of course, like I say, this is stylized. This is another representation of what I was just showing. This is a little bit more radical display of the difference between a low delta V flight path and a high delta V flight vector. In a case like this, basically you want to go to Mars and you can get there in 24 hours or less. You can just sort of look up and say, well, it's right there now, it's going to be over here in 24 hours, so we'll just aim this way and go. It reduces the navigation to that simple a problem. No more rooms full of computers and teams of scientists and engineers trying to work out this massively long flight path over a 2-year period because you're going to be there in another day. This is a velocity diagram for the scheme which I use in all 5 of my scenarios, and which is something which has been long desired by people who want to go to the outer planets, or the inner planets for that matter, where you accelerate halfway and decelerate the rest of the way. You're going to have basically a parabolic curve like so, up to here, and then start a new parabola here, so that looks like it's a little bit lopsided. Well, it should, because you have a vertex here, but now you have a vertex here. This is accelerating, this is decelerating, and your average velocity will be sitting around here somewhere. And this is going from Earth to Mars, or wherever you wish. This is the point at which you turn around your vessel or apply reverse thrust if you have engines that you can fire forward. This is Mars ship number 1. And this is where I get into my first scenario. I have a whole bunch of formulas here that I'm not showing because basically I didn't have room for the slides, but I have it here for anyone who wants to look at it afterwards. Table 1A, spacecraft statistics. Spacecraft mass, 50,000 MKS metric tons, which is some 540,000, I believe I've been saying 549, 540,499 FPS tons at mean sea level. This is a big ship. In terms of what this thing weighs, it'll give the Nimitz a run for its money. Overall dimensions, length by width by height, 1,000 feet by 390 feet by 180 feet. Rotating sections are 390 feet by 60 feet 4 inches. That's the 2 wheel-like objects on either end. These things are connected by an H-frame and turtle shell construction with what I call a bow tie section, obviously because of the space between the 2 coplanar rotating sections there. It has sort of the shape of a bow tie inside the turtle shell. All of that is in 0G, and it's roughly 40 to 50% of the vessel. This thing has a crew complement of 480 persons who are living in normal Earth gravity inside these rotating sections. There are 240 persons in each one. There's a crew weight allowance of 200 FPS pounds per crewman and 100 pounds of luggage per crewman. Consumable atmosphere is 350,400 FPS pounds of oxygen, 460,137 FPS pounds of nitrogen, with a mission capacity of 175,200 man days at 2 FPS pounds oxygen per day per person without recycling atmosphere. In other words, 365 days of continuous non-renewed atmosphere for 480 persons. Now you include atmosphere recycling and you can multiply times whatever this is. This is considerable capacity. Drinking water, 876,000 US gallons, which is some 7,026,247 FPS pounds. Mission capacity, 175,200 man days at 5 US gallons water per day per person without recycling water. This is all just consumables, and it has this kind of capacity. And that's all just in the rotating sections. That's not additional consumable stores you could have in the zero-G section, which you could transfer. Table 1B, mission statistics. Distance to Mars, average orbital separation, 2.608 times 10 to the 11th NKS meters. The ship's going to be accelerated at 0.01 G or 0.098 NKS meters per second squared. The reason for this is that if it were very much greater than that, you'd have sort of a variable rotating Coriolis force on all the people in the ship, so you have to keep the overall acceleration down. Now this is going to increase the amount of time it takes to get to Mars. Let's see what it does. With a mass energy conversion rate here of only 1%, which is low throttle in this machine, we have a fuel requirement one way of 1,568.5 FPS pounds. Now you could call that 4,409.2 FPS pounds both ways, with a 1,272.2 FPS pound reserve for maneuvering at each end of the mission. Here's the fuel flow rate. Get a load. 218 milligrams per second. Now, the transit time, Earth to Mars, what everybody's waiting for. 37 days, 18 hours, 1 minute, 10 seconds, one way. Meet that with a stick, with this kind of a ship. Scenario number 2 is basically the same ship, the same general capabilities, but with a K factor of 10%, the fuel flow rate is only 21.8 milligrams per second. Tiny amounts of fuel. Now, scenario number 3, scenarios 3 and 4, for which I don't believe I have any separate slides, I sure don't, which would be what you might call Mars ship number 2, which unfortunately I don't have illustrated here, would be sort of a conventional looking rocket, so it looked like any other generic looking rocket you've ever seen, just a tube of some kind with a nose cone and what have you. But let me tell you what it would be like inside. This scenario is a manned mission from Earth to Mars with a crew of 10 persons. Crew members are assigned private quarters enclosing 500 square feet of floor space. Decks are 15 feet apart and employ 8-foot ceilings. Each crew apartment has independent life support equipment dedicated to that apartment with the capacity to service 2 such apartments. Normal gravity is maintained throughout the manned flight area by the acceleration or deceleration of the spacecraft. The manned flight area is in zero-G at all times and the plasma thunder engine is not activated. Zero-G therefore will be experienced by the crew prior to departure from Earth, during the turnaround maneuver at mid-course, and following arrival at Mars. Accordingly, all crew quarters facilities are designed to work well both in normal gravity and in zero-G. Now, spacecraft statistics. 1,000 MKS metric tons, which is some 10,810 FPS tons at mean sea level. That's about like a tin can or destroyer in naval terms. Overall dimensions, it is 60 feet in diameter by 254 feet, 10.6 inches in length. Has 10 persons on board, 5 persons on each of 2 crew quarter decks. I allow 200 pounds per crewman, 100 pounds per crewman for luggage. Consumable atmosphere is 7,300 FPS pounds of oxygen, 9,586 FPS pounds of nitrogen. Mission capacity is 3,650 man days at 2 FPS pounds O2 per day. per person without recycling, or a year's capacity for 10 persons. Drinking water, 18,250 US gallons, or 146,380 FPS pounds of water. 3,650 man days at 5 US gallons water per day per person without recycling. Emission statistics. Distance to be covered, same as before, 2.608 times 10 to the 11th MKS meters. Average orbital separation, AOS. Acceleration is 1g, or 9.8 meters per second squared. Transit time. Remember the title of this paper? 3 days, 18 hours, 36 minutes, 7 seconds, one way. Mass energy conversion rate, 1% low throttle. Fuel requirement, 30,763 FPS pounds one way. That's because of the increased acceleration. 86,479.8 FPS pounds round trip with a 24,953.8 FPS pound reserve. Fuel flow rate, 4.362 grams per second. Getting up to the grams range now, that's enough to fill a thimble. The next scenario is the same, except the conversion factor is 10% and the fuel flow rate is 436 milligrams per second. Scenario number 5 is the one for which the paper is named. At this point, it's no surprise you can get to Mars in a week. This is a 115 metric ton single engine probe tug and payload from Earth to Mars in 7 days. Demonstration of fuel economy. This scenario involves a robot probe tug with 65 metric tons taking a 50 metric ton payload to Mars from Earth orbit in only 7 days using less than 50 kilograms of fuel with a K factor of only 1%, the low throttle setting. In other words, this is minimum on everything. It should be noted that the payload factor for this particular example is some 43.5%. What is it for most chemical rockets, for most missions of any kind, including lifting to low Earth orbit? If they get 18%, they're doing good, right? 20%, what was it? 10%?
The shuttle's 1%.
Yep.
That's all spacecraft.
Yeah, right. So the 18% is red hot. So this, we're talking 43.5% here to Mars. That you reuse the probe tug, it comes back. While the payload can be payload factor can be far higher, even this payload factor is unheard of for almost any other type of space transportation system where the current are foreseen for the future. This is especially true for a Mars mission, whether manned or unmanned. Spacecraft mass, 115 MKS metric tons, gross vehicle mass, or GVM, that's 1,243 FPS tons at mean sea level. Probe tug mass, 65 metric tons, or 703 FPS tons. Payload mass, 50 metric tons, or 540 FPS tons at mean sea level. Pretty hefty little gadgets even by today's standards, and this is the dinky ship of the 5 scenarios. Overall dimensions, diameter 25 feet, length 168 feet 10 inches. Crew complement, none. Mission stats, distance to cover, same as before. The AOS, 2.608 times 10 to the 11th MKS meters. Acceleration, 0.29 G, or 2.85 MKS meters per second squared. Transit time, 7 days, exactly one way. Mass energy conversion rate, 1%, low throttle. Fuel requirement, 1,029.1 FPS pounds one way. 2,500 FPS pounds both ways with a 441 pound reserve. And a fuel flow rate of only 78.7 milligrams per second. Now I'd like to point out that this 50 kilograms of fuel, in terms of gasoline, that's a little over 19 gallons. We're talking big engine, little fuel tank. Most vehicles today, whether they're chemical rockets or nuclear rockets, have little bitty engines, huge fuel tanks, and a little bit of payload. With Plasma Thunder, you've got a big engine, a huge payload, and a little bitty fuel tank. And that's what mass energy conversion can do for it. And it's the Newman effect of all things that makes it possible. Observations. With the advent of plasma thunder engine technology, former limitations on the speed, size, and payload capabilities of both manned and unmanned interplanetary spacecraft are reduced to an extent previously thought by most people to be impossible. Of course, some people still think the Newman machine doesn't work. I'm sorry, it does. But that's because most people don't understand the application of supersymmetry to what's going on in the Newman machine, which is also the key to the function of the plasma thunder engine. The first two scenarios in particular make this abundantly clear. The surprise comes with the third and fourth scenarios. It's revealed that Mars actually can be reached by a manned vessel in much less than a week using the plasma thunder engine. It is only the fifth scenario that the mission is designed specifically to require 7 days to make the trip from Earth to Mars over the average orbital separation distance. Out of all 5 cases presented, probably the single most remarkable observation that can be made, other than perhaps of the sheer size of the vessels in the first 2 scenarios, 540,000 FPS tons, is that the quantities of fuel required for Earth to Mars flight are virtually negligible, especially when compared to the sizes of the spacecraft. In fact, the single greatest advantage the plasma thunder engine possibly other than its ion engine class level specific impulse, is the extreme fuel economy as compared to any other conventional type of propulsion system. Now, something that hasn't been brought out is that plasma thunder can use just about anything you can put in it that you can ionize. If you can ionize water, it'll use that. If you can ionize methane, it'll use that. If all you have is mercury, that'll do. Hydrogen, helium, neon, whatever you can get your hands on. You find some frozen methane in an asteroid out there somewhere and you're out of fuel, get out there in a spacesuit with a pick, bust some off, toss it in the chamber, heat it up, and you're fuel. You've heard about these scenarios they have for Mars missions where they want to pre-land robot ships that are going to sit there and make fuel for the ships that are coming after them. The quantities of fuel that they are going to make would drive a fleet of these ships all over the solar system for years. Mars ship number 1, the big one. For years on end, they just stop by Mars occasionally to fuel up again. Also, the types of fuels that will be manufactured are suited to use in plasma thunder. They don't have to change anything. Go ahead and set them up. But instead of coming down there with conventional rockets and fueling them up and blasting back off Mars or however they plan to do that, use plasma thunder. That's all it takes. And then you can go anywhere in the solar system you want to go. Throttle control philosophy. There are people who have suggested, the last couple of days of discussing this, that one could use the fuel flow rate for throttle. I don't advise it because of the radical change in thrust you get with just plus or minus a couple of milligrams at most any K factor, even 1%. The K factor, however, can be controlled very, very closely. What K is simply the conversion rate matter to energy, where you take the total amount of fuel times K factor, and that's the M0 in your M0C squared equation. And M0C squared is then equated to 1/2 M sub S V sub S squared for the ship, mass of the ship and its velocity, because it's direct energy transfer. By the way, if you're wondering what the efficiency is, the K factor is the efficiency, minus the energy lost to proton generation at higher K factors above 10%, like the order of 50%. If in an actual flight engine you can get it that high. Now that'd be a pretty lengthy engine, probably several hundred meters in length. Now that's talking about building ships, which would make this Mars ship number 1 here look like a lifeboat. And this already has 480 people on it. This is big stuff. As you can see, I do not think small. What I call spam in a can. I don't waste my time with that. Save those things for life preservers. You know, NASA wants to stick people in these little plastic zipper bubbles for basically sort of like lifeboats in space. My idea is to use one of their current ships as a lifeboat. That's much more appropriate in my way of thinking. But that's just me. In summary, the application of plasma thunder technology to both manned and unmanned missions to the planets represents a tremendous gain and spacecraft size, payload factor, flight speed, and mission duration capabilities heretofore considered to be nothing more than the stuff of dreams. As shown in the scenarios presented, serious missions to Mars need no longer consist primarily of small robot craft on flight paths requiring 2 years or longer in the space environment. We just lost one that way. It was out there so long the valves froze up, something exploded, and the stupid thing never did work. They lost it, what, 2/3 of the way to Mars, the Mars Observer. That was last year. It seems like the more of that kind of stuff they do, it's like they're becoming unexperienced as they go. They're de-evolving in their experience. I don't know what it is. It's now possible to send very large-scale manned missions with massive supplies and equipment not only to Mars, but also to the rest of the outer planets in a matter of days or weeks rather than months or years. Since the Plasma Thunder propulsion system is the result of a technology integration, and this is the important part, the engineering of a flight prototype can begin at once. There's nothing new to develop. This does not require the research and development of some new technology that we don't have yet. Everything is in hand. I plan to have, however small, however meager, however mediocre, a functioning model prototype of this engine in New York next year. Come hell or high water, as they say. If I have to crawl and carry it on my back, I'm going to be there with it. And I plan to demonstrate it. I don't know how impressive it's going to be because it's liable to be a little bitty thing. It probably won't do much. It'll probably be difficult to measure the performance of it, to tell much difference between what you have in the plasma injector and what you have in the exhaust. But basically, I'll probably have to do that by putting some gauges on the coils and then doing some little demonstrations I do with the little Newman machines I built where I can prove that there is energy output from the plasma because of the interaction in the interactor, and that will be demonstration enough that what I'm claiming occurs does in fact occur. So, we take these 7 technologies I mentioned before, we put them together, and we have this engine. And all of these technologies exist, and they all work. And there's no reason they will not work together. There are a couple of things that I don't have in the paper here, which are rather interesting. I sent an article into Ad Astra about Plasma Thunder. I called it Plasma Thunder Real Star Power. And one of the missions I suggested was a probe to Alpha Centauri, because this thing will get you there in about 15 years, using fairly conservative parameters. Of course, it'll take 5 years to get the telemetry back, but you can send a massive probe tug with a canister with like 100 huge, triple nuclear powered probes in them, with those little, what do they call those little nuclear reactors they had a few years ago?
RTGs?
Yes, RTGs. Yes, you could have probes of such size that only 4 of them would fit in this room, and put 100 of them on the ship and send them to Alpha Centauri and go ahead and see what's out there. If one probe doesn't work, launch the next one. You find a bunch of planets, fine, put 5 or 10 probes down on each one. Just make sure you have channel capacity to carry all that stuff and relay it back, preferably from a central relay. The other mission that I suggested would be something which would make solar mats look like an exercise in remote sensing. And that would be to have a solar probe, which would be launched directly into the sun, but what you would do is you would fly out to about the orbit of Jupiter, then you would turn around and, as they say, put the throttle to the firewall and just make a suicide run directly at the sun. The idea is to take advantage of the fact that because of the specific heat of any given material, there is a certain minimum time required for that material to incinerate, however hot it may be outside. I don't care if it's millions of degrees of plasma heat outside, nuclear plasma. It will take a certain finite amount of time for a material to incinerate because of specific heat. Because otherwise you've got physical law violations all over the place. Talk about thermodynamics. What this thing does is fly into the corona and impact with the photosphere. While it's in the corona, explosive charges, or whatever you want to use, are firing out sensors, going out like popcorn going off, like machine gun fire. They incinerate perhaps in only a few milliseconds or a few hundred milliseconds or however long, but the digital technology we have today, which is ferociously fast, can take 100 readings in that length of time, take 100 pictures, right up close, as they say, in your face, right at the surface of the sun, inside the chromosphere, inside the solar prominence. Let's see Solar Max do that. Solar Max wasn't equipped to do anything of that nature. It was flying around at somewhere out near the orbit of Mercury, rotating at extreme speed to keep the instruments from burning up. It was a nice trick for its day, but like I say, it's remote sensing compared to what you can do with plasma thunder, because plasma thunder will get you going so fast that your velocities will be nudging the relativistic regime by the time you enter the sun. You'll have a sensing window of less than a minute. In that length of time, you take all the readings you can, and you just keep repeating the entire catalog of digital information, one massive burst after another, until the spacecraft is finally destroyed either by being incinerated by the heat or impact with the surface of the sun. It's only with something that can go really fast that you can do that, and plasma thunder can get you that speed, and with a considerable payload. You can put a whopping heavy shield on this thing. Speed and payload, that's the name of the game in this business. Now, what about using plasma thunder as an HLV? I don't advise it. The exhaust is radiation. Hard radiation. Hard EM radiation. It will fry your tail feathers at a distance. This is for use in space only. And at that, you don't crank it up near space stations or other spacecraft, especially if they're not, they're in the exhaust cone. And if you're going to use very high K factors, well over 10%, you've got to watch the neutron radiation. You'll have to have a shield between the engine and the payload at high K factors. At low K factors, you don't need it. But low K factors can do a lot. Because look at what all I've just described, using K factors of only 1% and 10%. This kind of a thing. A 480-person vessel that weighs 540,000 tons. That's a big dude. I doubt seriously anything like this is going to be built in the near future, just for the sheer politics and nothing else. My opinion of how to get to the outer planets right now, basically, is to develop a good HLV like the Delta Clipper, and to get plasma thunder online for going planet to planet. And that will get us all over the solar system like that. No more years to the outer planets. We can go out there and check up on Voyager and see how it's doing, make some adjustments and fly back. The same week, literally. That is something which I think is nice to know we can do now, technologically at least. As far as the cost, the plasma thunder engine is not an expensive proposition. However, since it's a spaceborne type of propulsion system, that means you have to get it up there first. Since if you want to do something big with it, you need a big engine, you need large-scale space construction. I have on previous occasions addressed that topic. So getting it set up won't be cheap because you have to use the methods of hand, and they are sadly expensive. So there is that little hurdle to cross. But once it's crossed, hey, we're home free. Where do you want to go? How fast do you want to get there? How much luggage do you want to carry? Name it. Any questions? Yes.
I have a couple of questions. First of all, now, how much do you think it's going to cost to build it? You didn't say specific amount.
Are you talking about
Plasma thunder system.
an actual ship? I have not addressed cost at this point. I have addressed performance. I can do cost in a subsequent paper.
Also, in your demonstration model, will that put out gamma radiation or?
I would not allow it if it could.
What?
I'm not going to do anything dumb, you know.
What? I missed the question. Could you please repeat?
Oh, yes. I was just asked if the model of the plasma thunder engine I plan to have in New York is going to emit gamma radiation. If it can, I'm not going to let it do it. I mean, you know, I'm not going to say that, hey guys, look at this, and then irradiate everybody. Duh, you know. No, I don't think so. I doubt seriously that the model I'm going to bring will be capable of that sort of thing. I mean, if I can get the plasma to just, go 2 or 3 times as fast as you can with the injector, I'll be thrilled to get that much out of it. Because it's going to be a little tube this long, something I can carry in the luggage.
Will you do it outside or do it inside or?
I would imagine that with a suitable backstop and so forth, it could be done inside. It won't take much shielding. So basically just to keep somebody from getting, toasted with some flying electrons. It'd be sort of like walking in front of a plasma torch, I would think, if you were walking too close to the exhaust. Because it will have a fairly hot little output, but the idea basically is to show that the technology functions, and then to show that I can vary the K factor, that you can increase the thrust in the fashion that I described with this mutual field hyperdeclension I've talked about, and that you can project this kind of performance for bigger engines. That you can build a flight engine that can propel this kind of a ship. By the way, these are your engine tunnels here and here on this vessel. And you have basically the head of an engine facing that way and that way here, that way and that way here. These fire together and these fire together. They can be single engines or clusters. There's another advantage to these engines. Every part of them, except of course the inside of the plasma tube, is accessible in shirt sleeves. That's a nice thing about it. I don't know any spacecraft built at present where you can get out and do anything with the engines without going EPA. Yes?
With high dilution of reaction mass per amount of fuel, the Robertel forward concepts were your figures for amount of mass converted via annihilation, but adding in tons per amount of that of the surrounding mass, so that you could get a cool enough exhaust for near surface operations.
Oh yeah, that'd be almost like operating in what you might call a high bypass mode,
Yes.
like in a jet engine. That's a thought. You could do that sort of thing. You could carry along some water to blow into it, I guess.
The economics of launch is the absolute reason for that to be the highest priority. You don't want to pay $1 billion to get into space anymore.
Right. Well, still you would have the, even if you were to use this as a heat source for a steam rocket, still you've got the radiation in the exhaust to deal with, and they didn't like what they got out of Nerva. That's negligible by comparison.
Is it purely gamma? Is it purely photons? No nuclear particles?
It's at low K factors, well below 10%, it's liable to be mostly electromagnetic, and it's going to be just ions. X-rays and that sort of thing. But if well above 10%, upwards of 50% higher. Yeah,
neutrons and not highly energetic nucleons. Not
probably
highly energetic neutrons, protons, and exotics.
Right, yeah, because that would be at higher K factors like 25 and above. These scenarios here are for K factors of 0.1 and below. So it's conceivable that you might get away with it, but I have a sneaking suspicion the EPA would never allow it. If the EPA is still around by then, if you get what I mean. Dude's got his sights on them, yes.
Oh, first, a clarification. This is more efficient the longer your engine is?
Yeah, well, the thing about it is that you do have a critical length, because you see, the longer the interactor is, the greater the acceleration of the plasma, but then some plasmas will be intrinsically more efficient, will interact better than others. Also, there's the matter of reaction mass, because you are, in the end, accelerating mass. This is still a reaction drive. We're still talking Newtonian, or what in another paper I did was called quasi-Newtonian type 2 propulsion particle emission. But basically, running high efficiency fuels with a shorter interactor is probably the best way to go. But a longer interactor can handle anything you can put in it. I wouldn't want to get crude about what all you can put in the fuel tank, but basically you can use anything you can get your hands on with a long interactor. Of course, now if you put a high efficiency fuel in a longer interactor, you probably end up having to shut down aft sections, and you increase dead weight. But the dead weight in this case is not terribly significant. You see, that's one of the things about this engine is you can computer configure this engine for whatever kind of fuel you're using and for whatever kind of mission you want to fly. And it's throttleable from practically zero thrust, or that is to say just the output of the plasma injector itself, all the way up to whatever the maximum is on the engine, your top K factor for a given fuel flow rate. And you can also, you use your fuel flow rate basically to set your maximum thrust with whatever your highest K factor is that you use, and you vary your K factor because you can finely control that because you've got at least 3 different things you can control electronically, which is to say the field strengths on your coils, the switching frequencies, and the frequency ramp which is increasing frequency, switching frequency as you go down the tunnel, because it gets faster and faster and faster as you go. You've got a low frequency at the front end where the plasma injector is, and a high frequency at the aft end. Yes.
What kind of exhaust velocities are we talking about?
Photon drive.
Yeah,
Light output.
it's about the size of it.
Better.
Yeah, basically, if you were to take, you take some quantity of mass and take out 10% of that, you've got 90% of that mass left, and however much of that 10% was converted completely to energy, however fast that thing will go, plus whatever the initial velocity was out of the plasma injector. That's how fast that exhaust will be going. It's going to be trucking. The K factor, it would be probably, if I had to guess, it would be something in the order of K factor times C. But that's only a guess. I'd have to stop and calculate it to see. Yes.
Could you put your diagram of your new machine back up?
Yes, sure will.
And maybe explain a little bit about that?
Yeah. Back to it. There.
Yeah.
Okay, what'd you like to know?
Everything.
Oh, okay. Basically, what happens in this case, now you notice I'm showing inductors with a fixed magnet. This one is not rotating. Now, in an actual Newman machine where they have the rotating permanent magnet, the rotation of the permanent magnet contributes, as my experiments demonstrated, to voltage regulation. But you can basically do without that by just choosing a suitable frequency, driving frequency here, with a fixed magnet. Now, also, when you're dealing with the rotating magnet, the more of the inertial mass of rotation is vested in the permanent magnet, the better the voltage regulation, as opposed to having, say, half of it in the permanent magnet, half of it in the dead weight flywheel somewhere off the end of the shaft out of the action. But in this case, where I have a fixed permanent magnet, you can simply deform this field by driving this when Q1 is forward biased and this is shut off. Then when this is shut off and this is forward biased and this coil is shorted, this will undeform very fast and will do external work, or try to, against this.
So is it an accelerating, kind of a alternating current that are you talking about?
Yeah, that's basically what's happening. And the energy source is, or at least I am theorizing at this time, because I know there's one there, and this is the best I have for an explanation, is that it is the intrinsic energy of the weak nuclear field. You know, you have some that you can draw off without an atom coming apart right away. That comes from something that I've called the honeybee hypothesis, that, you know, atoms constantly not only give off but also accumulate energy, and they keep more than they need to retain their structure and function. They can give off considerable energy without losing their basic infrastructure. And you can draw off weak nuclear field energy through the electroweak coupling, and that ends up going out to the external world through the magnetic field through the electron spin conserved under supersymmetry, which allows electron spin to act as an energy gateway and still have the properties of conservation. Supersymmetry, by the way, is described mathematically in terms of graded Lie algebras, which are Lie algebras for which both rotations and anti-rotations occur simultaneously.
You have another question?
Yes.
Mark?
You can do all this with off-the-shelf hardware?
Yes. You see, that's the nice thing about it. I built 2 of these little gadgets using, like I say, toy Mabuchi motors from Radio Shack. Mabuchi is a Japanese manufacturer that makes little toy motors you use in model airplanes, little cars and tanks and stuff.
You're saying it
Motors or engines?
Motors, electric motors,
Electric
permanent
motor.
magnet motors, yeah.
You're saying you could also use it to make power.
Yeah. Joseph Newman's been using a machine, one of these rotating machines to power his house for some years. He's been doing that since the late 60s, early 70s, I forget. A long time ago. I went to Jackson in 1985 to see a demonstration he did there. It was impressive. I held one of the functioning machines, it was a fan, in my hands. I picked it up off the table because I thought, aha, secret cords under the table. Nope, sorry, no secret cords. I picked it up, nothing under it. It had 3D cells and it ran all day. Not only that, it was running faster when I left than when I got there. And I was there from at 9:30 in the morning, and I left at 5:30 that afternoon. He had streamers on it. They were like this when I arrived. The batteries were half dead. They did that. I learned that as I left. The batteries were half dead when I got there, and he turned the things on, and they had just enough energy to start the fans operating. And then as the fans operated, the fans being modified as Newman machines, they had his little commutator on the back. There was a guy from Japan taking very close-up pictures of these things. Taking some very, very studied pictures of them. The streamers were straight out when I left. Freakiest thing I ever saw, but it worked. So like I say, when you're looking at a black box where you put in a certain amount of energy, you get more out than you put in. The only way your first and second laws of thermodynamics can be true is if there's an energy source in the box. Otherwise, you're looking at some sort of contradiction. But if you've got the thing in front of you and it's doing it and you can't make it go away, you have to think. There's an energy source in the box. Find it. You have laws which will deal with it, but the trouble is most people don't know them. And when it comes to literature about these sorts of things, like the Newman machine, like supersymmetry, stuff like that, I find that a great many people, the biggest and loudest critics of this stuff can't name one paper. Or for that matter, they can't name 3 journals anyway, even in their own fields. But it's, I've had 25 years of running into that kind of thing. The people who know the most about it, who understand what's going on, are steeped in the literature, and they've read it back to the turn of the century and this sort of thing. And they know what's going on. They know why people back in Einstein's day thought what they did, things like that. And they understand where things like concept of the light barrier came from, that I did a paper on earlier this week, Yes?
Do you have a good reference on the Newman machine?
First of all, his book, just to see what he himself says. Then there's a fellow in Silver Spring, Maryland by the name of Paul Bruney, B-R-U-N-E-Y. He's the guy who first figured it out. And I had gotten a lot of my source material from him.
But he thinks it's slow proton decay rather than the electron.
I had attributed that idea to him in a subsequent conversation lately. He just said that he didn't recall that being his idea. I think what it was is something he said gave me that idea, and I asked him about it one time, and then in my faulty recollection, I thought it was something he told me. He thinks it is the heat in the magnet itself, but I've done experiments which, to me indicates clearly that couldn't be the case. That and the specific heat would be too much of a bottleneck. This is just because the indication is that the output of the machine has no upper limit. Of course, the odd thing about that is that a pocket-sized device, or one the size of this room, would have the same upper limit. It's kind of bizarre, although the thing about it is the larger machine would last longer. That's the difference. Of course, the thing about this is your interface can be only so small and still transfer, power from source to load. So you have limitations like that. You have Thevenin-Norton limitations, things of that nature, impedance matching, and you have certain physical sizes of things which are associated with that. So that is not true in an absolute sense. It's just a theoretical indication based on an experiment without taking those things into account. But when you take them into account, oh yeah, a bigger machine will give you a lot more power a lot longer.
Excuse me, Mark.
In actual fact.
We have to shut down because we were only here to 3:34 and we have to clear. I appreciate it, but we have to do what they tell us to do, so appreciate you all stopping in.